started along.
And particularly, we went through what the situation was if we're dealing with multi-component ideal gases. And so we're ready actually now to take a look at vapor-liquid equilibrium in the multi-component ideal systems and to derive for you what you've seen before as Raoult's law. This is a little bit of reading here, pages 367 to 373. Now, what we know is if we want to consider a process at constant temperature and pressure where a number of moles dNi of liquid transfers into the gas phase, we can consider the change in free energy for that process, because what we know is that is zero if we are at equilibrium. And I can write that out as my partial molar Gibbs free energy of component I here in the liquid phase. So actually it's going to be, we're going to go to the vapor phase, so let's do it that way. dNi, then minus the liquid will have lost that amount of Gibbs free energy. And I'll change the notation to Gibbs notation for these partial molar Gibbs free energies, namely I'll use the mu's. So what I have here is mu I for the vapor minus mu I for the liquid times dNi, and this is what is equal to 0. So you see that for equilibrium here, that mu I in the vapor equals mu I in the liquid. And we saw that before when I used the fact that the pure component G's were equal to each other as a basis for deriving the Clapeyron equation. But now what I want to do is to establish the equilibrium criterion here for a component I moving between a vapor and a liquid solution. So what I need to do is to expand these out. Let's move that here. Can I write these out if I'm going to assume here an ideal system? Clean up my writing here a little bit. Then I have for the vapor chemical potential for the pure vapor plus RT log YI was among the things that I had derived earlier. And that's now going to be equal to, for the liquid, the chemical potential here for the pure liquid plus RT times the logarithm of XI. Now I'm assuming it's an ideal system, so not only have I got an ideal gas in the vapor phase, I'm assuming I have an ideal solution in the liquid phase, and that means that I can write the chemical potential out this way. In other words, just use the same idea here of mole fraction, but now that's mole fraction in the liquid phase. Now I want to be able to simplify this thing, but what I need to recognize is that these pure component chemical potentials for the pure vapor and the pure liquid cannot be canceled out because they don't refer to the same pressure. Let's just write it all out here. This is, oh, writing's terrible. This is equal to the chemical potential of vapor, of pure vapor, at its actual equilibrium vapor pressure. And this is equal to the chemical potential of pure liquid at the pressure P. So these are chemical potentials at different pressures. And in order to be able to ultimately cancel them out, because they don't refer to equilibrium of the pure component, I need to adjust the pressure of this vapor phase from PIS to the actual pressure of the system. So let's take a look at that. right here. Now that's what I need to evaluate. So to get this, I don't know how far you are, familiar you are, but you could put, just by inspection, write that down, but let's build the derivative and do all the steps. So we start out with so there's my fundamental equation for the Gibbs free energy. In this case, it's the chemical potential. It's got all at constant temperature, so that is 0. And because it's an ideal gas, I know that the molar volume of the pure vapor I is just RT over P. So if I want to build the derivative, I'll divide through by dP. And I see that this derivative is just RT over P. Yeah.
What's the first character in the term that you crossed out? Is that an S?
First character in what?
SI.
SI, that's the pure component molar entropy of
Okay, well, I
component
was just
I.
making sure it was an S.
Yeah. I'm just writing the fundamental equation for a DG quantity.
It's not the system pressure or the partial pressure, RT over P.
System, the P without any decoration is the system pressure. PIS is the pure component I vapor pressure. So this is lots of stuff to write here. This whole thing then is just this. So if I want to go back and write the equilibrium equation, I'm going to flash back for just a second and then come back to this. But this is what we want to write out, this thing. So now I'm going to replace this with what I've now got it, with the term adjusting it to the pressure of the system. So now, let's just write it above here and then I'm going to repeat what I had on the previous page because we can't just go back and look at it. And now this is the thing that we now have. So it's been replaced by this. I've now adjusted it. Now it's good because this vapor pressure, this chemical potential of the pure saturated vapor at P cancels out with this pure component chemical potential for a liquid at that pressure P. So what I am left with is this. I can knock RT out of every term. I can combine these logarithms and I get log of YIP over BIS equal log of XI. Or when I exponentiate that, I end up with what you all recognize as Raoult's law.
Did the RT natural log the composition terms, did they come from isothermal pressure changes? Where did they come from?
Yeah.
They came from isothermal
Yeah.
pressure changes. So this whole derivation takes place
All
at
the constant temperature.
constant temperature. Okay.
Okay, we're ready now to, well, let me make some comments about Raoult's law here first. It actually applies in some cases, but they're very limited. When the components are chemically nearly identical, like, let's say water and D2O, something like that, or to some extent toluene, benzene, you'll get an effectively an ideal solution, but those are quite rare. So the use of Raoult's law is quite limited. So what we're interested in now is extending it to a consideration of non-ideal solutions. Actually, they can be non-ideal, the systems can be non-ideal in two respects. I may have a vapor phase which can't be considered an ideal gas mixture any longer, although for most cases of interest to us, that's pretty good. But almost never do we have an ideal liquid solution. So we need to consider broadening it and at least do the formalism of saying how we express the existence of this non-ideality. So I want to consider phase equilibrium now in ideal, non-ideal systems, and that leads to the introduction of the property that we know of as fugacity. And the reading for this, a little bit more here, 391 to 404. So in order to express equilibrium, we need to express chemical potentials in various circumstances. So let's consider how we do that. For ideal cases, we can write the expression here for d mu I, and if we're going to let it be ideal gases here, let's remind ourselves of that fact. This is all at constant temperature. This was just mentioned. Then d mu I is equal to this, or RT over P, dP, or RT d log P. We've seen that before. This is for pure I. And for I component in a mixture, then what I have here is going to be this convenient way to do this is to just write the expression I've got for the integrated chemical potential. Let's write that all out. And I've got the expression for this above, that's just the pure component, chemical differential of the chemical potential written up here, so that is and then I'll continue to write this. Let's drag it all out here. kind of saw that result coming. So for our ideal systems, d mu is equal to RT d log P. For a component I in a mixture, it's RT d log of the partial pressure, which is very convenient for solving problems in equilibrium problems in these ideal systems. But what Gian Lewis suggested was that we retain the same format that we have here for expressing differentials of chemical potentials, but introduce a new adjusted variable. And what he did was the following. He said, let's write now d mu I 0 without a star by it, so not an ideal gas system. You'll write that down in the same format, RT d log, but now not pressure, but a thing he called fugacity. And I'm assuming now I'm dealing with pure component I. And for a component in a mixture, so no zero, RT d log fugacity of that component in a mixture. And the notation is we designate that with a circumflex over the top. So a mixture or a solution. And so note this notation. Okay, what I want to do next is show how the direct relationship here between fugacity and chemical potential is expressed in these terms, and then I want to address what the physical significance of this fugacity function is, because it's very important to our understanding of the way we're going to handle this whole situation. So, let's note that we can so I can write just here in general that d mu I, whatever it is equal to RT d log fugacity, which means if I integrate that mu I in some state 2 minus mu I in some state 1, whatever those are, is equal to, just in general, RT logarithm of fugacity here in state 2 over fugacity in state 1. So this is just in general true. Now what that does, it doesn't really complete the definition of fugacity yet. You can sort of imply what it is, but we complete that definition by making the statement that as the pressure goes to 0, so that we recover ideal gas conditions, which we always do if the pressure is low enough, that the fugacity turns into pressure or partial pressure. So we note that as P goes to 0, that means we recover ideal gas conditions, and we can make the statement that the fugacity goes to the pressure, or the fugacity of a component I in the mixture goes to the partial pressure. Now we have it complete. And we could integrate from a low pressure condition to whatever condition we are interested in using equations like this, and define for ourselves what are called the fugacity coefficients. So Bi here is defined as the fugacity coefficient of a pure component I, and it's defined as the fugacity over the pressure. And of course, you note that as we go to ideal gas conditions, that goes to 1. And the fugacity coefficient of component I in the mixture is defined as the fugacity of component I in the mixture over the partial pressure, which is YIP. So these can be regarded as definitions, and we'll be seeing them over and over again. Well, we should talk a little bit about this thing that we invented, this fugacity, and discuss its physical significance. First of all, what are its units? Pressure. So we another thing to note is it has all of the information that we have in chemical potential. So if we know the fugacity, we should be able to calculate the potential and vice versa.
Could you, what's the first sentence you wrote?
Is units of pressure.
Okay.
Terrible writing, but I am saying it while I do it. And as Lewis suggested, he said it represents the true escaping tendency of the component from a system. So let me write that down and then discuss it a bit. Now for ideal gases, the pressure is the escaping tendency. Let's just draw a little diagram to make that point. So if I have an ideal gas in a system like this at a pressure P, that pressure represents how badly or how strongly that component wants to get out of the system. And I think that should be intuitive. And if I have a component I in a system, and I have it bound by walls that are permeable to component I, that this partial pressure represents the escaping tendency of that component I from the system. So that's escaping tendency for ideal gases. Now let's think about it for a moment. If the gas is not an ideal gas, but it's another one described by perhaps one of the equations of state that we have, then the true escaping tendency might not be as large as the pressure P, for example, because there are, on the net, intermolecular attractive forces that kind of hold it back. So if we correct for that, then we can use as the corrected pressure or corrected escaping tendency the fugacity. So the idea is here, if I wrote the same thing down here for real gases, and I could write the fugacity here, and I'm assuming it's gas I, that represents the escaping tendency for this pure component I, corrected for non-ideality. And the same would be true if I had, say, some component I in a mixture. Then rather than partial pressure, I would have the fugacity of that component in the mixture as my true escaping tendency. Is everyone more or less comfortable with this? So we have an idea of what fugacity is. Now, since I made the assertion that it contains all of the information that is in the chemical potential, what I'm suggesting is that we might be able to express equilibrium criteria in terms of fugacity rather than in terms of chemical potentials. And there's some advantages to that. This seems to have shut itself off, of course. Yeah, and maybe I got it back. But fugacity, I think, is a lot friendlier to work with. First of all, it has an absolute value. Chemical potential does not. As an energy quantity, chemical potential has to be reckoned relative to some reference state. Whereas for fugacity, it is what it is. It's an absolute value. And it's a physical quantity having dimensions of pressure that I think are easy to conceptualize. So it might be more convenient for us to formulate our equilibrium criteria in terms of fugacity rather than chemical potential. Chemical potential always lies in the background. We saw that the difference in chemical potential between a pair of phases is a measure of how much the component wants to go from one phase to another. In fact, the difference in chemical potential can be thought of as a driving force for that process, and hence the notation, that's why we call it a chemical potential. But now what I'm suggesting is that fugacity might serve as a more convenient expression for this equilibrium criterion and hence driving force for the process of mass transfer. So let's clear up that assertion. For phase equilibrium then between a vapor and a liquid, I might be able to write this as my equilibrium criterion. And let's look at, I think, a useful analogy for you. If fugacity is the escaping tendency of a component I to go from one system to another across a boundary which is permeable to it, then I've drawn that picture here, and we'll have transfer from the left to the right if the fugacity of that component in the left chamber is higher than the fugacity of that component in the right-hand chamber. This is a direct analogy to what we have for the definition of temperature, which is also a measure of escaping tendency, but in this case, escaping tendency of thermal energy. So we saw if the temperature in the chamber on the left is higher than that on the right, then we expect to have a heat transfer from the left to the right. Everyone see that analogy? Well, what I'd like to nail down now is the fact that the quality of chemical potential is equivalent to the quality of fugacity, so that we can use a criterion like this to express our equilibrium, and then we'll go from there for real systems. So my task here is to show that. Let's say mu I in some system alpha equal to mu I in some system beta is equivalent to fugacity of that component I in alpha equal to fugacity in system beta. Well, let's work it out. I can write this out in accord with the expression that I had earlier. This can be written as mu I alpha, a lot of notation here to keep track of in the reference state, plus RT times the logarithm of fugacity of component I in system alpha over its fugacity in the reference state. And that would be equal to same expression now for system beta. Well, I can rearrange this a bit. Let's write it this way. We'll bring this term over to the left. Let's put this up. You see, I've just taken the logarithms that were here in the terms in the denominator and just shifted that over to the right. Now what I notice is that these two terms cancel each other out. I can divide through by RT, exponentiate both sides, and I've got what I was after. And no physical approximations as a rigorous expression. So what our job now is to, if this is going to be the situation, and we want to solve equilibrium problems of all kinds in terms of the fugacity, our job is to be able to develop expressions for the fugacities of components in all situations. So we want to be able to evaluate the fugacity in all types of situations. So let's write down what those situations might be. Simplest one is going to be for pure gases. Next one is for a component